Good morning, students. Welcome to this class. In this class, I am going to teach you Hamilton's canonical equation in terms of Poisson bracket, or it is otherwise called as special cases of Poisson bracket. In the last lecture, I explained you about Poisson bracket. Poisson bracket is nothing but a function whose Poisson bracket with the Hamiltonian h vanishes, then that function is a constant of motion. We saw already in the earlier lecture. That is, according to Poisson bracket, a function whose Poisson bracket with Hamiltonian vanishes, then that function is a constant of motion. This we will know. According to Poisson bracket, a function whose Poisson bracket with Hamiltonian vanishes, then that function is a constant of motion. Mathematically, we may write this as f comma h is equal to 0. F comma h is equal to 0. Also, mathematically, we may write the Poisson equation as bracket of f comma h, that is equal to, tell me, summation of I dou f by dou qi dou h by dou pi minus dou f by dou pi dou h by dou qi. This equation we already saw in the Poisson bracket itself. Also, we know another equation, Poisson bracket of f comma h, that is equal to df by dt. That is this equation. How this equation came? Poisson bracket of f comma h plus dou f by dou t is equal to 0. When f is not explicitly depend upon time, then this dou f by dou t will become 0. Therefore, dou h Poisson bracket of f comma h is equal to 0. We saw already. Similarly, here this equation you see, that is f comma h. When this term comes here, this is otherwise df by dt. That is dou f by dou t minus dou f by dou t. F comma h minus dou f by dou t is equal to 0, or f comma h is equal to dou f by dou t. Okay, we already saw these equations. You make it this equation number 2. Therefore, using these two equations 1 and 2, now I want to calculate the canonical equation in terms of Poisson bracket. Canonical equations in terms of bracket. Poisson bracket. We already saw canonical equations, 3 equations, canonical equations, 3 equations. One is qi dot value, another one is pi dot value, another with respect to time and Lagrangian, Hamiltonian and Lagrangian. You just verify that video and notes. Now, we want to calculate this value now. Using this equation 1 and 2, I want to derive canonical equation in terms of Poisson bracket. Now, how it will be happen? For this, we will substitute, we will use 3 cases. That's why it is otherwise called as special cases of Poisson bracket also. Okay, so how it will be derived? Now you see, case 1. Now, case 1, that is we want to calculate first canonical equation from Poisson bracket. How? In terms of Poisson bracket. How? Just let f is equal to qk in equation 1. Let f is equal to qk in equation 1. So equation 1 becomes instead of f you make it qk. So qk comma h, that is equal to summation I dou f by dou qi, here dou qk by dou qi into dou h by dou pi, there is no change, minus dou qk divided by dou pi into dou h by dou qi. Understand? That is, in the place of f you are substituting qk in equation 1. That's all. You see here, instead of f you are substituting qk, here also you are substituting qk. That's all. This is the first case I am making. F is equal to qk. Now you see, so when solve this, qk h, that is equal to summation of I, this qk, partial derivative of qk and partial derivative of qi is represented as delta, called Kronecker function, delta. Here the term is k, here the term is I, therefore delta ki. In the subscript you write is delta ki, where this delta is called as Kronecker function. This is a new function name, you just remember it. This is the delta Kronecker function. Delta, this term is like that only, dou h by dou pi minus. Here delta qk and delta pi, this is the position vector variable and this is the momentum variable. There is no relationship between this position variable and this momentum variable. Therefore, these both are independent to each other. Therefore, this term becomes 0. That is, when qk and pi both are independent of each other, differentiation of these things will becomes 0. Therefore, delta qk by delta pi will become 0 into dou h by dou qi. Understand? So here delta dou qk by dou qi is represented as a function called Kronecker function. If here k and here I, then you may write as ki. If here I and k, then how this will be written? Delta ik. Okay. So you just remember and just see the things. If this script superscript here qk, here I is there, therefore this function Kronecker function may be written as delta of ki dou h by dou pi minus this dou qk and dou pi both are independent to each other. So when you are partially you are differentiating these things, it becomes 0. Therefore it is 0 into dou h by dou qi. So this equation, how this equation becomes now? Qk of h, that is equal to summation I delta ki dou h by dou pi. That's all. This term becomes 0. Now you make this equation number 3. Okay, right. Now when here in Kronecker function, when in the Kronecker function, when k is equal to I, when k equal to I, then this delta ki becomes 1. When this k is not equal to I, then this Kronecker function will become 0. That is, now when k that is, you may write like this: delta ki equal to 1 when I is equal to k. This delta ki becomes 0 when this I is not equal to k. So this is the condition. Kronecker function will equal to 0, that is I is not equal to k. That value becomes 1 when I is equal to k. Now consider k is equal to I. Now consider k is equal to I. So now what will happen for this third equation? K is equal to I, that is q k of h, that is equal to summation of I delta k, instead of I you want to make it k, then dou h by dou p k. Okay, so qk of h is equal to this equation 3 becomes qk of h, Poisson bracket of qkh, that is equal to summation of I delta kk dou h by dou pk, or qk comma h, that is equal to dou h by dou pk, dou h by dou pk, that is this, where Kronecker function of the same variable will becomes 1. Therefore delta kk is equal to 1. Though if there is no I term, therefore I am removing this summation of I also. Therefore this term will become qk of h, that is equal to dou h by dou pk. Poisson bracket of qk and h, that is equal to dou h by dou pk. Okay, this is one equation. You make it this equation number 4. Understand? So what I did, I substituted f is equal to qk in equation 1 and I solved the things, and I got here Poisson bracket of qkh is equal to dou h by dou pk. Okay, so this is equation number 4, you understand. Now put f is equal to qk in equation 2. There are first two equations I have taken. One is the mathematical expression of that Poisson bracket f comma h, that is equal to dou f by dou qi dou h by dou pi minus dou f by dou pi dou h by dou qi. So that is equation number 1. Then I have taken another one equation, that is dou f by f comma h, that is equal to, you see the second equation, you see here f comma h is equal to df by dt. Here instead of f you substitute qk, instead of h, instead of f you substitute qk. Therefore that equation 2 becomes qk Poisson bracket of qk of h, that is equal to dqk by dt. Okay, or qk of h, qk comma h, that is equal to dqk by dt is nothing but qk dot. Okay, so this is another equation. You make it equation number 5. You see, verify, you compare equation number 4, equation number 5. So what will happen? qkh, that is equal to qk dot, that is equal to dou H by dou Pk. Now you compare equation number 4 and equation number 5. In equation number 4 also there is QKH. In equation number 5 also there is QKH. But in equation number 4, QKH that is equal to dou H by dou Pk. Here QK dot. So comparing that equation 4 and 5, we get QK Poisson bracket of QKH that is equal to QK dot that is equal to dou H by dou Pk. You see this is what? Canonical transformation equation. QK dot that is equal to dou H by dou Pk in terms of Poisson bracket QK of H. Okay, QK and H. Understand? So this equation 6 represents canonical equation of motion in terms of Poisson bracket. So this is the first equation in canonical motion. Then another case 2. Another case 2. Here you substitute F is equal to Pk. In the case 1 you substituted F is equal to Qk. Now in the second case you are substituting F is equal to Pk in the equation 1, and the same process what I did already in previous, we are doing the same only now also. Okay. Okay, now I will write the equation. So equation 1 become, now equation 1 become, that is in the equation 1 now you substitute in the place of F you substitute Pk. Therefore I once again I will write equation 1. That is equation 1 is nothing but, for your understanding I am writing again Fh that is equal to summation I dou F by dou Qi dou H by dou Pi minus dou F by dou Pi dou H by dou Qi. Similarly this is equation number 1. Then equation number 2 we know Poisson bracket of F comma H that is equal to dF by dt. Okay, this equation. Now I am substituting in the place of F, I am substituting Pk in equation 1. So in equation 1 if I am substituting Pk, equation 1 becomes Poisson bracket of Pk comma H that is equal to summation of I dou Pk by dou Qi dou H by dou Pi minus dou Pk divided by dou Pi dou H by dou Qi. This is equation number 7. I make it. Now here you see Pk Qi. This is the momentum term, this is the position variable, this is the momentum variable, generalized momentum variable. Therefore these two are independent of each other. So partial derivative of dou Pk by dou Qi becomes 0. Therefore Pk of H that is equal to summation I, this first term will becomes 0 dou H by dou P minus, here you see this is Pk and Pi, so both are dependent of each other, so it will be represented as the Kronecker function. Therefore delta Ki dou H by dou Qi. Understand now? So this equation may become Pk of H is equal to, this term becomes 0, therefore minus summation of I delta Ki dou H by dou Qi. Now the same procedure what I did already. This equation number, you make it equation number 8. So what is the equation? Pk H that is equal to, that is a Poisson bracket of Pkh that is equal to summation of I delta ki dou h by dou qi. Now when I is equal to k or k is equal to I, this term becomes Poisson bracket of pkh, that is equal to minus summation of I, this becomes 1 and dou h by dou qi. Sorry, dou qk. Instead of I, you may substitute k. So dou qk, or this equation will be written as pk of pkh, from Poisson bracket of pk comma h is equal to minus dou h by dou qk. So this is one equation. Equation number 9. Similarly, what I did already, in the place of, in the second equation, that is in the here, this is the second equation I already taken. Poisson bracket of f comma h is equal to df by dt. Here, now you substitute in the place of f, you substitute pk. You substitute pk. So what it will come? Pk, that is equation 2, becomes pk of h, that is equal to dpk by dt, or this dpk by dt is nothing but pk dot. Okay. Therefore, how you may write this equation? By comparing equation, this is equation number 10. Now by comparing the equation 9 and 10, by comparing the equation 9 and 10, how we can write this equation? Poisson bracket of pk comma h is equal to pk dot, that is equal to minus dou h by dou qk. This is the another canonical transformation equation. This is another canonical transformation equation. So in the first case, I have substituted f is equal to qk and I derived one canonical equation, transformation equation, in terms of Poisson bracket. Afterwards, in the case 2, I made f is equal to pk and I derived the canonical transformation equation, second canonical transformation equation with respect to Poisson bracket. Okay. Now that is, so I have calculated two canonical equations. Now there is another case. You substitute, there is another case, that is in the place of f you substitute h. In the place of f you substitute h, that is it is case 3. In the case 3, you take this equation, that is df by dt, that is equal to f comma h, that is Poisson bracket of f comma h plus dou f by dou t. This is the Poisson bracket equation we already saw. This is equation number 12. Okay. Here in case 3, here you substitute f is equal to h. You substitute f is equal to h. So in canonical transformation, to derive the canonical transformation equations, I have taken two equations. One is Poisson bracket equation mathematically when it is expanded, that equation. Then another equation is Poisson bracket of f comma h, that is equal to dou f by dou t. We have taken the two equations. Here now I am taking this equation df by dt, that is equal to Poisson bracket of f comma h plus dou f by dou t. Here now you substitute in the place of f, substitute h. So what will happen? dh by dt, that is equal to Poisson bracket of h comma h plus dou h by dou t. Now dh by dt that is equal to, now you expand in terms of Poisson bracket. How you will expand? Dou h by dou qi, then another term is dou h by dou pi minus dou h by dou pi, dou h by dou qi plus dou h by dou t. These two terms same, so cancels each other. So dh by dt, that is equal to dou h by dou t. That is, time derivative of a Hamiltonian function is equal to the partial derivative of Hamiltonian function h. Both are same. Time derivative of Hamiltonian function, partial derivative of Hamiltonian function, both will become same. Also, this dh by dt we may write as h dot, that is equal to dou h by dou t. This is another one important equation we found out from these Poisson relations. From these Poisson's relations. So, in this class, I have derived 3 equations. 2 equations are canonical transformation equations in terms of Poisson bracket, and this case 3 is the special case. Here I am calculating, here I derived that the time derivative of a Hamiltonian function and the partial derivative of a Hamiltonian function, both are equal. That is h dot, that is equal to dou h by dou t. These are called as canonical transformation equation of motion in terms of Poisson bracket, or special cases of Poisson bracket. In question paper, in what format they are asking, you may write these equations. Okay. So, I will meet you with another topic in the next class. Okay. Thank you.